Well, hello friends. Welcome back to the JavaScript bytecode project. Today we're just going to continue. So if you haven't already seen parts 1 and 2 of this series, I definitely recommend starting at the beginning so that you have full context. But basically we are building a bytecode virtual machine for our JavaScript engine. And today we are going to implement loop support. So stuff like while loops, for loops, and that's going to require some support for jumping back and forth in the bytecode. And yeah, so let's just get right into it. We'll make a little test program here that, like, the simplest possible thing, right? So while I is less than 3, then increment I by 1. Something like that. And if we just try to run that, then it should fail to generate bytecode because we have nodes that are new. So yeah, missing generate bytecode because we now have a while statement here, which we are not familiar with yet. So let's go and add a generate bytecode overload for while statement. Generate bytecode, bytecode generator. Okay. And oh, I was thinking maybe we should actually move the bytecode generation stuff from the big ASD file, because this is like over 2,000 lines. It's a bit heavy to edit. I was thinking we should just move it to a separate file. So let's just do that. We'll put it here in the bytecode directory, even like call it like AST code gen CPP. And then it doesn't have to be so chunky in the editor. Also, this looks weird. Bytecode AST cogen. Okay. And then we can take all of these generate bytecode overloads and just bring them over there, is what I was thinking. Lib.js ASTH. Namespace.js. Yes, here we go. Okay. Yeah, and we'll get rid of all of the bytecode stuff in AST.cpp. I think that's a nice improvement, and we can update this with a clean slate copyright. Okay, that's cool. So, yeah, let's just make sure that everything builds here, and then we can commit that separately before we continue. Blah, blah, blah. Oh, right, because now I added the while statement thing without actually implementing it, so that's on me. Yup. And yup. Lib.js move. AST bytecode generation virtuals to separate CPP file. This will hopefully make it a bit more pleasant to edit this as both this as both this and AST/CPP. As things will just get larger and larger, let's say. Yeah. Right. So now we can get back on track and implement the while statement. So returns optional bytecode register, of course. While statement, generate bytecode. So what on earth do we generate for a while statement? Well, a while statement has two things, right? It has a test and a body. So first thing we got to do is we got to evaluate. We got to run the test expression, and if it evaluates to true, then we need to run the body. But if the test expression evaluates to false, we jump over the body and continue after. So this is something that we cannot currently express with the bytecode, but we'll add a way to do that. So I guess we start by running the test. So the test generate bytecode generator, and then we don't. Oh well, the result of that, we do care about the result. So test result register, and then that needs to be passed to some kind of conditional jump. So like generator emit jump if false, let's say. Or it's tempting to call it like jump unless or something like that, but jump if false seems more expressive. So jump if false, test result register. Oh, and this is going to be an optional actually. So let's just do a verify here and do that. Bytecode up, jump if false. Sure. And then the problem is, like, we want to jump over the body to the end. So like, where do we jump to? Like, we don't know where that is yet, because first we have to actually produce the body. So mbody generate bytecode in the generator, sure. And at this point, I think I'm just going to start doing this because I remember in the last video I was complaining about how this just feels so much better than maybe unused dir is same thing, right? Like, yeah, I'm tired of maybe unused for that pattern. This is so much nicer. So we don't have a target yet, so we can't give it a jump target. But once we've generated this code, now we have a target. So we want to jump to here. So I guess we need to update that instruction. So let's add a way to get the instruction we just created here. So like test jump, let's say test jump, and test jump set target, generator. I guess we'll make a label here. Yeah. Let's see. Okay. So we evaluate the test expression first, and then we do a jump if false to jump past the body. Otherwise, we'll run the body. and I guess we need to loop also. So after the body, before the end target or whatever, test jump, before the ending of it all, we need to loop back to the beginning so that we can go back to the test. So should that be like the test label? So the test label is generator make a label and then emit a, I guess here we just want an unconditional jump. So like just jump to the test label. Does that make sense? I feel like that makes sense. Okay, so let's see if we can let's see if we can do this. So first we need emit to return a reference to the emitted instruction. So we'll just do something like that since we are moving it here. And we can make a commit out of that separately because it's so small and simple. Make bytecode generator emit, return the instruction, created instruction, yeah. You know, we can add a little bit more context here. This will be useful for instructions that need to be modified later on during code generation, i.e. jumps. Okay. And then we need to add, so we have two new instructions. We have jump and jump if false. So jump, public instruction, and take some type of label, which we haven't invented yet, but I mean, a label is just a reference to somewhere in the bytecode stream, right? So essentially just an address. Yeah, that will be simple, I think. Target, let's call it. Label target, and let's make that explicit. And let's add an H file for that, sort of like we did for register. And let's see, label, but I think label would just be a size T. And instead of index, we will call it address. Oh, that didn't work. All right. Well, no big deal. And let's do a formatter for it while we're here. Why not? Maybe colon? That's kind of nice. Like colon and then the address. Could also do at, but I like the colon for labels. Reminds me of, I don't know what it reminds me of, NASM or something like that. Right, so we need to include that in places. Right, so let's include label, and same thing in the generator. Let's also add label, make label. Maybe it would just be like return m block, wait, instructions size, like, yeah, because I think that's essentially what a label is, right? It's just wherever we are right now in the instruction stream that we're emitting, the address of the next instruction is effectively a label to here. So yeah, we can just emit or just give you that. Okay. And jump. Oh, it's, wait, what was the problem? Oh, it's abstract, right. Well, we just need these. Jump, and we also need jump if false, which I guess, wait. So that needs to have a condition, but, well, the condition is a register. Wait, so, wait, how does this work? I just want to see the AST. So we have binary expression with the less than operator. Binary expression execute. So if you do what we currently do for less than is that we call less than and pass in the left-hand side and the right-hand side. And less than, oh, it just returns about, right, it just returns a value. And yeah, so it returns a value that's either false or true. That's straightforward. So, wait, so then we just need to act on that. So this is not terribly complicated. So register result, I guess. And then, let's see. But we don't have the labels, so let's make that maybe like this. And something like that, actually. And then we just need the result like this. And wait, so what did we say? Set target, right? So set target, optional label target, m target is move target. So like that. Okay. So that feels like it makes sense. Oh, maybe I didn't do that label thing fully correctly here. Yeah, just need to copy paste a little bit better. Oh, and this thing needs to return something. While statement execute. What does it return normally? Last value. Do while statements need to return something? I'm unsure. Maybe they do. Last value is whatever the last time we executed the body. I mean, we can replicate that behavior. So that goes here, like body result reg, return body result reg. Yeah. It's interesting how these pieces just kind of fall into place. Like I've never worked on, or I've never built like a compiler before, so this is really interesting to see how this sort of makes sense, because I know about these abstractions and I know that there are so many of them already implemented, right? So it's just interesting when you take something, a well-known abstraction, and then you try to implement it and everything just kind of fits. It's a lot of fun to see that, and it really helps me understand things better. So now that we do this, then can we compile? Incomplete type bytecode block. Oh, in the generator. I guess that was optimistic that we would see the block here. So, but we can put this out of line. It's not a big deal. Label generator, make label. Okay, so just some linking problems, I guess, because we need to actually implement these opcodes. So starting with jump to string. Well, we made a formatter for it, so we can just do like mtarget like that. And for jump if false, it's we have a result, and then we also have a target. Although the target is optional, so maybe we need to have two separate branches here. So something more like that, or I don't know, like that. Like if it's not set yet, I'll say empty. And how do we execute these instructions? So we don't have a jumping mechanism in the interpreter at the moment. So if you recall, the way we made the interpreter is that it just loops over the instructions in order. So I guess this has to change a bit. And let's do something like we have a program counter. I'm abbreviating that to PC because it's such a common abbreviation. Usually I don't like abbreviations, but for things like PC, I think it makes sense. So the PC needs to, I guess, wait, what am I trying to do? We'll grab the current instruction at the PC. We'll execute it like normal, and then we'll increment the PC. Maybe what we should, let's have a failsafe here, like while PC is less than the number of instructions in the current block. So this is what we had before, basically just expressed differently. And then how do we know that somebody wanted to jump? So I guess one way is that we could have execute return if the instruction wants to jump. That would be one approach to it, I guess. So like change the signature to like optional size T, and this, if there is something here, then it wants to jump to there. Optional label, maybe. Another alternative would be that the interpreter would have sort of a jump slot, which could then be filled in and checked here. So like if m pending jump as value. Yeah, let's do it this way. This is not super elegant, but I don't know what's the best way to do this, and I don't mind hacking it this way for now. We can certainly change it if we think of a better way down the line. So this will just be a optional size T pending jump. Yeah. And then if there is such a thing, then we just take it into the PC and continue without incrementing the PC. It's a little bit ugly, but not that bad. And then here we can simply say ending jump is label address. Wait. We need to see that here. Yeah, that's okay. And then in the execute here, we simply say interpreter jump to my target. Boom. And in the jump if false, we have a result that we have to check. So first we have to read that register. So reg m result, and then if not result as bool, then we gotta jump. So interpreter jump to target value. Yeah, and also like if you're executing, this thing should absolutely have a value in the target. So let's verify that, because it would be a programming error if that's not the case. Oh, the binary expression, right. So we also have to add the less than operator here. So binary op less than, and then we'll emit a bytecode op less than. Same as the add and sub, really. Yeah. So this one is super straightforward. Could almost make a macro for these. Maybe that's what we'll end up doing later, since they're so repetitive. But for now, we can just copy paste. Not a big deal. And less than. Less than. All right. Okay, so did this work? Like the output is a bit is not the most user friendly. So let's see. Let's look at the generated code here. So right, so this is our program. I set I to 0, so we're loading a constant 0 into register 1, and then assigning that to variable I from register 1. So that's I equals 0, or this one right here, taken care of. And then comes the while loop. So let's see, here's the head of the while loop, I guess. So get variable I into register 2, and then the value 3 into register 3, and then compare 2 and 3, store the result into register 4, jump if false for register 4 to target colon. Oh, the colon looks so weird. Yeah, we should, maybe the colon, leading colon was weird. We can come up with something better. Okay, so jump to 11 if the result is false. So 11 is actually past the end, but that kind of works out because there's nothing there, but the loop will just exit at that point. So it's actually legal to jump past the end. I don't know if that's necessarily healthy. Maybe we should, I don't know, like maybe we should put out a no-op or something at the end. We may end up doing something like that later on if we want to enforce some invariant that like every label has a corresponding instruction. But for now, I think that's okay. Okay, so jump if false, and then otherwise where's the increment? So here's the increment. Get I, and load 1 into reg 6, add 5 and 6 together, store in R7. So R7 is then stored into I. So if R7 reaches 3, which it does, register 7 reaches 3, that means that we must have looped all the way. But let's just make triply sure. And let's print out the PC while we're executing. So here, and then we'll also do something like jump to okay, so execute, shmexecute, jump to 2, jump to 2, jump to 2, and then at the end jump to 11. That's nice. Like this unconditional jump here at the end is pretty cool. I like that. That looks neat. Let's, however, fix this. So instead of saying colon, maybe at is the better thing. And I was thinking, should we use like dollar signs for the register numbers? But I don't know if that would look cool. Would it look cool? Let's test it. With stuff like this, it is important that you make things look cool because we are going to be staring at this bytecode a lot. So it seems important to make it look sweet. Did this help anything? I guess I kind of like it, actually. Jump at 2. Yeah, that's kind of neat. Okay. Let's go with that. So JS print bytecode register with the format $num instead of $num. Yeah, because why not? Let's go with that. And then let's see. So what have we done now? Now we have invented the label and we added less than. So I guess we could, I was just thinking, should we do some of these things separately? We can do the less than operator separately, actually, because it's self-contained really from all this other stuff. So where is less than? Right here. Nope, yes, nope, nope, and yes, and nope. Okay. Web.js and less than bytecode instruction. Okay. That's nice and straightforward. And then let's see, lib.js. Oh, wait, back up. Let's fix all these print statements that we didn't need. Yeah. libjs. Add basic support for while. In the bytecode engine. Yes, this introduces two new instructions, jump and jump if false. Jumps are made to jumps are made to a bytecode label, which is a simple object that represents a location in the bytecode stream. Since the target of a note that you may not always know the target label of a jump when when adding the jump itself, adding the jump instruction itself. So but we can just update the instruction later on during cogen once we know where the jump target is. Yeah. That's a little muddy, but that's probably okay. And yeah, I feel like that's okay. So jump, the bytecode interpreter now implements jumping via a jump slot, which jump slot that gets checked after each instruction to see if a jump is pending. If not, we just increment the program counter as usual. Yeah, okay, so I think that's okay. So what's another loop? I guess we could I was thinking if we should do a for loop, or we could also do while instead of just while. So if we make a do while loop, that would be something more like, I don't know, like, let's go the other way. While I is not equal to 0, and then I is 3, like that. When we get to, it's nice to have some extra things that we have to implement, because then we get some random things done at the same time. So do JS. Oh wait, shoot, where am I? This is not where I normally put my test files. All right, so now we have a do while statement instead, and a not equal binary expression. So, well, let's just get back into it. The AST needs to have generate bytecode in the do while statement. And then we need to implement that. So let's just start with the while statement. So the difference, of course, is that with the do while statement, we unconditionally run the body once at the start. And then we have the test at the end instead. So let's see. So we just want to first emit the body, although we want to make a label. So we'll call the label like the head. And then the test goes at the end. So we put the body out. And then we do the test. And then we jump to the, we don't need to update it afterwards then, because now we know we're just jumping to the head again if the thing is true. So this goes the other way around. Yes. So we need a jump if true to complement the jump if false instruction. Jump if true. Sure. Jump if false. It's just the other way around, so just inverting that condition there. And other than that, it's very, very straightforward. So just doing this, and that. Cool. Okay, and now we're failing on the binary expression once again, so let's do that one. So what's the thing that we're adding now? It's the binary op equals, I guess? Wait, is it abstract equals? Or wait, no, it's not equals. Wait, what do we call that? Is it abstract in equals? I gotta see what we print as that. It's abstract in equals. Okay, all right. Abstract in equals, sure. Generator emit bytecode op abstract in equals. Let's just do that. Like we can have one of each for these things. I think that's probably okay. And then in some future world, then it might make sense to consolidate some of these things. I'm not exactly sure. You could, I do feel like you could probably do something where you have like a comparison, like less than, followed by a jump. Like you could combine those two things, right, into something like jump if less than, and that would be a single instruction. And I think that would probably map, or is that valuable? I feel like that could be valuable. But let's not get ahead of ourselves. I'm try to stay focused on what we're doing, because like my brain keeps trying to go in all kinds of directions with this stuff, and it's important to stay on course. So for the abstract in equals binary op, we just again abstract in equals. Every time I add one of these, I think more and more maybe they should be a macro. But let's chill out on that. Just another moment. Abstract in equals. So do we have abstract EQ, and do we just run that backwards, or how does that work? Abstract in equals. What do we do when we execute it? Yeah, we just do a value from the negated or whatever. So value from that, and boom. Wait, so what did the program do? I forget. We start at 3, and then we loop until we reach 0. So I feel like that completed. So let's see. Abstract in equals. Jump if true. Jump. Yeah, that's so cool. This bytecode is like really cool looking to me somehow. Like I've never made up my own instruction set before, so this is really quite fun. So we're just checking here if register 6 has reached 0, and register 6 has indeed become 0 in the end. And 6 is the... Wait. We're checking if register 6 is a constant value 0. Sorry. We're getting I into 5, and then comparing 5 to the constant 0, and storing the result in 7. Okay. Which is false at the end. Yeah, so I think this is executed correctly, because we do have I and 5, so these are equal. That's why the program halts, or stops, let's say. So if we say, well, if we don't do anything, it should just run forever, right? And it does. Let me out. Okay, very, very cool. So let's, I guess, again, do the abstract in equals opcode first, just because it's nice and separate. Lib.js, add abstract in equals, oops. Okay. Do I need to do that? Yes. Abstract in equals bytecode instruction. Bloop, bloop, bloop. That's pretty cool. You don't like the word in equals? I don't love that word either, but is that a spec word? Let's look it up. Abstract in equals. In equals is weird. In equals JavaScript. That might not be a spec term. Okay, well, let's hold off on adding that to the dictionary, because now I'm confused. But let's instead just add bytecode generation for the do while statement, which turned out quite nice as well. And I keep alternating between writing my commit messages in CLine and in Vim. I don't know why. There's no rhyme or reason. I just keep jumping between the two. I guess I want to use CLine, but muscle memory is so strong that I keep ending up in the command line commit editor. But I want to be here because I have my nice spell checker and everything here. Anyway, bear with me. So, generate bytecode for 2 while statements. This was quite straightforward, using the same label jump machinery as we added for while statements. The main addition here is a new jump if true. The main new thing fitting on the line. The main addition here is a new jump if true instruction, bytecode instruction. Yeah, that's really it. Really cool. So, I think maybe this is enough for this video. So we'll round it off here. We've made some nice progress today on while and do while loops. So now we can do jumps. The execution is no longer linear, and we can jump conditionally based on the result of comparisons. So nice progress. And I guess if you made it this far, then I thank you for watching and for hanging out. I hope that you saw something interesting here. I personally find all of this super duper interesting. Just to finally engage with this. I think I always kind of considered these things a little bit too difficult for me. Even when I was around JavaScript core while working on WebKit, I would work on the CSS parts of WebKit, for example, or the DOM parts, and then I would see all the people working on JavaScript core, and I would see these tree dumps and ASTs and bytecodes and JIT logic and whatever, and I kind of had this idea that, oh, that's too complicated for me. I don't know how that works, and I'm just gonna stick to my my more simple web engine stuff. And it's nice to go through this process now that we're doing here, to sort of it's almost like I'm showing myself that this is not that complicated, because I do have some weird like latent hangups about it or whatever. So thank you very much for joining me while I go through this process of showing myself that this is perfectly doable and understandable and so on. Yeah, so thanks for checking out the video, and I will see you in the next one. Bye.